Hello all, this is Anand Kumar again and welcome to my video lecture series number 2 in this operating system process series. And in this video lecture series, we'll just continue with the last class continuation. In the last class, I think we have seen about, I'll just scroll it for your reference. In the last class, we have seen about the representation of process scheduling, that is a process enters through a ready queue and through the processing unit, it goes through the IO request, that is nothing but input output request, and then it goes through the input output queue, and then it goes to the input output devices, and of course and loop is completed. And after getting to the next loop through the processing unit, it goes to a time slice period. Suppose if the time slice has been expired, it will be again re-looped, and after the third loop it goes into the process of called as forking. That is, forking is nothing but giving a sub aspect, that is from the main aspect. I mean to say, a sub process has been created through the main process, and forking a child means a child is given a new birth from a parent. That is what we call as a forking in this operating system concepts. So next loop will be like, and suppose considering an exception happens or an interrupt happens or interrupt occurs, it is stating as waiting for input, and that process will be getting into the waiting for an input queue. So next is, we'll just start with this term called schedulers. Schedulers are of many types, and we have just taken two types for our reference here. One is long-term scheduler, that is job scheduler, and the next one is short-term scheduler, that is nothing but CPU scheduler. So coming to the long-term scheduler, this selects which process or which processes should be brought into the ready queue, and the short-term scheduler, that is nothing but CPU scheduler, it selects which process should be executed next and allocates the CPU. So coming to the addition of medium-term scheduling, so suppose consider a partially executed swapped out process is there, and it has been again swapped into the ready queue, and the ready queue has been considered as what we call it as another process, is again reprocessed through a CPU, and it has been swapped out, and that has been partially executed, and then again it is given to the ready queue. Suppose if this process is being completed, it just passed through the input output device and the input output waiting queues. So coming to this continuation of the schedulers, the short-term scheduler is invoked very frequently, that is in milliseconds, and it must be damn really fast. And the next term is what you call as long-term scheduler, and it is invoked very infrequently, that is in terms of seconds and minutes, and it may be considered as a slow one. And the next one is the long-term scheduler controls the degree of multiprogramming, that is the process can be described as either input output bound process, and another one is CPU bound process. Input output bound process is nothing but it spends more time doing the input output works than the computations and many short CPU bursts. Coming to the CPU bound process, it spends more time doing the computations, very long CPU bursts. So next is the context switch. Coming to the context switch, when CPU switches to another process, the system must save the state of the old process and load the saved state for the new process. Context switch time is overhead, and the system does no useful work while switching. It's time dependent and on hardware support. So considering the context switching, we can see it in the video games. That is, suppose if we enter a level, that level has been saved and will be processing through the second level. And if suppose we are getting out in, or if we are supporting getting if we are getting killed in the second stage or second level, we might not even play the first level in the first place, and we'll just right away enter from the second level in the second place. So next is process creation. The parent process creates child process, and which in turn creates another process, forming a tree of processes, and it is considered as like it has been used in resource sharing and in execution part. Coming to the resource sharing part, the parent and child share all resources. Next is another case, that is children share subset of parents resources, and the next case, parent and child share no resources. The execution part has parent and child execute concurrently, or the parent waits until the child or the children terminates. So this process creates address space, and we have some Unix example. In the address space, the child is the duplicate of a parent, and the child has a program loaded into it through a parent. And considering the point of Unix usage, fork system call creates new process, and the execution system, that is the exec system command call, is used to fork to replace the processes memory space with a new program. And I'll stop with this today, and we'll see you in the remaining in the next.